Hello, everyone. Welcome to today's webcast brought to you by Robo Global at Vetify. I am Zeno Mercer, research lead covering robotics, AI, and healthcare innovation for the Robo Global indices here at Vetify. Today, we will be covering, as the title says, what trends to watch in robotics and AI, and specifically, what are some of the technologies coming together and what impact will they have on our lives in various industries and society. And we brought a special guest today, which I'll introduce shortly, who will be covering these topics. Throughout this presentation today, we'll have an opportunity to ask questions. We want this to be interactive. To do, simply type your question in the Q&A box. It should be located on the bottom right corner of the screen. These slides and a recording of today's webinar will be made available. You will receive an email when they're available, and you can also download a copy of the presentation in the folder widget in the bottom of your screen, along with some additional materials. There's a survey that you can be completed at the end of the presentation that is located in the media player below, or you can click the clipboard widget that is located at the bottom of the screen. Included also are a couple of questions asking for your feedback. We really appreciate your input and opinion. And lastly, if you are here, you can click on the certification widget if you're here for CE credit. So if you're looking to receive that, a green check mark will appear when you have completed everything needed to receive that. So now I'd like to introduce our special guest today. She's a strategic advisor here for Robo Global. Dr. Daniela Roos is not only a professor, but she is the director of MIT's Computer Science and Artificial Intelligence Laboratory, CSAIL, as it's commonly known, which is one of the world's leading AI and robotics research labs. She is a pioneer in the field of robotics and artificial intelligence, and her research focuses on developing flexible autonomous systems from modular and self-configurable robots to soft robots and swarm robots, self-driving vehicles, and mobile sensor networks. Her work has influenced industries ranging from healthcare to transportation, with innovations being commercialized by companies like iRobot and Boeing. This year alone, she has authored 2 books, The Heart and the Chip and The Mind's Mirror. She is also the co-founder of Liquid AI, which spun out of her lab, and is coincidentally doing a major public product launch later this week, which I am looking forward to attending. Daniela envisions a world where AI and robotics empowers people in the world around us, something which she often refers to as magic and superpowers, which I also fully ascribe to as well. So without further ado, thank you for joining us today, Daniela.
Thank you for that really generous introduction. Let me see if I can get the tech to work. Let's see, share. And can you see my screen?
Yes, I can see your screen. I think we were going to maybe start with a polling question. I'm not sure if that's being able to be seen right now. But
so I should stop sharing?
Stop, yeah, we'll get to this in a second.
1 second. Stop sharing, okay.
That was a preview for everyone, a sneak peek. So I wanted to get a sense from everyone here today. This was a pulse check for Daniela and myself, but how are you using AI or not using AI? Are you using ChatGPT, note transcription tools? Just trying to get a general sense of how people are using this. And if you're not using it, if you're wanting to, or you're against it. And leave this up for a couple seconds more. So please get these answers in, and then I will move to the next slide here. Okay, so this is how the cookie crumbles. All right, Daniela, can you see that?
Yes, very interesting.
So 32% for personal and professional use. That's pretty...
42% nothing at all, but interested in exploring. And so this is super interesting.
It is. And then I'm gonna quickly go over, just for those that are new here, and we'll tie back into that. But just for those who don't know, Robo Global is the pioneer of the world's first robotics index, which was launched in 2013. And now we cover and classify and score companies based on their innovation, market leadership, technical leadership. And then in 2018, I helped launch our artificial intelligence strategy, TH&Q, as well as HTech, so healthcare innovation. So these are 3 areas that are near and dear to my heart and that we cover through 3 indices. The broader team, Daniela, is one of our advisors that help us guide us and envision where the world is heading, where the puck is heading, what technologies matter, and which companies are really not just the leaders of today, but what will be the leaders of tomorrow. And just generally speaking, this is our outlook, not Daniela's, but we're really seeing a convergence of robotics, AI, and energy coming together and very symbiotically supporting each other and growing. The economic impact we expect to have a growing share of the economy, whether that grows or decreases. And you might say, why would the economy decrease? There's a lot of excess spending in areas that we don't need. There's a lot of inefficiencies in healthcare. So technically, we could even see some deflationary pressure there, which I believe would be strongly beneficial. There are a lot of multiple $100 billion, if not $1 trillion markets coming around. And one of the reasons why this is happening is this technology advancement is accelerating very rapidly. And we're entering what we're calling this multimodal revolution, where the way that humans understand and reason is now being extrapolated into robotics and AI. And we're also seeing favorable policy. Now, Daniela here today is that point, the multimodal AI revolution. She understands this. To be able to train and build these models and understand this, you have to understand the world and how the technology works. And Daniela bridges these together excellently in practice. So our last poll before Daniela will get started is just from what we've covered and where your head is at, what categories of AI and robotics do you believe, before Daniela gives her presentation today, where do you see the world heading? What do you want to have the most impact? And we'll leave this up for about 10 more seconds before we get going, and then I will fully hand it over to you, Daniela. So going forward now. Okay. Looks like we have a lot of people excited about advanced robotics and automation and some healthcare. All right, Daniela, what do you think?
That's amazing. I am so excited to share with you the latest and the greatest in these spaces today. And in fact, as you mentioned, the 2 books I wrote this past year, I wrote these books especially for people who are interested in learning more about AI and robotics and basically the state of the art in these fields. Yeah, it's very interesting. Not so much education and personal productivity. A lot of interest in financial services, a lot of interest in robotics and automation and biotech. But there are opportunities to use these technologies also in the areas that are flagged as 0% response rate in personal productivity and in making the world a better place.
Yeah, I agree. I'm really excited about kind of the AI for personal AI assistance. Yeah, with that, let's feel free to share your screen.
Amazing. Amazing. Let's see. Hello, everyone. I'm so delighted to be here with you. And today, what I wanted to tell you about is a new trend in robotics and in AI, which I call physical intelligence. And this is when AI's power to understand digital text, images, and other online information can be used to make real-world machines smarter. And as I mentioned earlier in the session, I recently wrote 2 books. The blue book, called The Mind's Mirror, is a book that introduces the world to AI, introduces the public to AI. So this is not a technical book. It's a book that aims to demystify AI, what it is, what kind of capabilities it can bring to individuals, to businesses, to society, and how it works also, so that you can have a better understanding, because by understanding conceptually how it all works, you will have a better sense of how it can be useful. The Mind's Mirror also has a chapter that is called the AI Playbook, that helps companies go through a template, through some blueprints to determine how AI can be useful for you. And then we also talk a bit about what the risks are and what we can do about them. And then there is the analog of the for AI, which is robotics. And the book, The Heart and the Chip, really talks about a world where robots can help us with physical tasks. So if you look at these two technologies together, broadly speaking, AI and robotics are really powerful for today and for the future, because with these technologies, we will be able to support people with cognitive and physical work. And the technologies that are helping us in these directions are essentially three interconnected technologies. On one hand, we have robotics, which puts computation in action. And then we have AI, which gives machines the ability to make decisions and reason. And then we have machine learning, which is a field that cuts across both AI and robotics. And it's about using data to make better predictions. Right now, in the field of computing, AI and robotics are two largely separate fields. AI is amazing us with its decision making and reasoning, but it remains confined inside computers. It brings capabilities for the digital world. On the other hand, we have robots that have a physical presence and the ability to execute pre-programmed tasks. But robots are mostly not intelligent. Robots are mostly pre-programmed. Every move that you see in the dancing robots that have delighted all of us has been very carefully specified with careful descriptions of every trajectory those robotic limbs make. And so to me, what's exciting is that the separation is starting to change, because with great activity by the robotics community, AI is beginning to break free from the confines of 2D computer screen interactions and enter a vibrant 3D physical reality. And moving AI from the digital world into the physical world means that we can make physical machines intelligent. And this transformation is leading to what I call the next great breakthrough in AI, in other words, physical intelligence. And again, physical intelligence is when we use AI's power to understand text, images, and other online information to make real-world machines smarter. And so this means that AI can help pre-program machines, but not just robots. It can also help medical devices and sensors and power grids, anything with a physical component. It can make these installations do their jobs better by using knowledge from data. And so, for instance, with physical intelligence, we don't just have AI that gives us cognitive capabilities inside our computers, but we have AI solutions that are beginning to walk and fly and interact with us in the physical world. So just imagine robot helpers at the supermarket. Some are helping to stock shelves, others are helping us carry a box like the one on the left, and others, like the autonomous shopping cart, is helping a blind person navigate in a complex world. Now, in order to make this vision work, in order to make it all work, we really need to innovate on how AI thinks, and then what kind of machines are available to us. In other words, how machines are designed, and also how machines learn. And this is what I want to share today. Now, for physical intelligence, we need small AI brains that can run on the small computers that fit on the body of the machine. And here you can see the body of a robot fish we built in my lab. But today's AI does not fit, because today's AI is all about these huge capable models that require server farms. In addition to that, today's AI makes mistakes. And for example, you can see here the AI system of a robotic car that does not detect pedestrians. On the left, you see the camera image, and on the right, you see the AI system that can clearly detect the cars and the trees and the light poles, but does not see the pedestrians. And the reason it doesn't see the pedestrians is because the pedestrians are a group. They're not individual people that can be clearly distinguished. In this image, the group of people seems like a connected blob, and that does not look like what a person looks like. And since the machine learning systems have been trained with individual people, it's hard for them to detect the groups. So this is a problem. We don't want robot cars to mislabel images like this one. So these are important challenges that we are tackling using inspiration from nature. In particular, inspiration from a worm called C. elegans that has inspired a lot of the neuroscience literature to date. Now, in stark contrast with the billions of neurons that we have in the human brain, the worm lives happily on only 302 neurons. And what's really extraordinary is that biologists understand how these neurons work. They understand the math of the computation within each neuron and also the math of the interconnections between the neurons. So then here's an idea. Can we use the math of the worm neurons to build a new class of AI algorithms we call liquid networks? And so liquid networks are compact and explainable approaches to AI as compared to today's solutions. Liquid networks use a different technology than today's solution. Liquid networks are nature-based and physics-based. And let me explain to you what they are first in an application. So this is our self-driving car. The self-driving car was trained using a traditional AI solution, the type you find in many applications today, the type you read in articles today, in newspaper articles. And so the car seems to do pretty well. It's driving pretty well. But here is the dashboard of the computation of this car. Now, in the lower right corner, you see the map the car traverses, and in red, you see the path of the car. In the upper left corner, you see the camera input stream. And the big box with the blinking dots is the decision-making engine that tells the car how to steer. And this decision-making engine has tens of thousands of artificial neurons. It is impossible to correlate the activity of these neurons with a car's behavior. And furthermore, if you look in the lower left corner, this shows the attention map, which means where in the image the AI engine looks in order to make decisions. And you can see that this attention is very noisy. It's focused all over the road, and the regions with high intensity are the bushes and the trees on the side of the road. But that's not how people drive. Now contrast this with our worm-inspired liquid networks solution for self-driving cars. This is the liquid network AI brain for a self-driving car. This solution can drive a car using only 19 liquid neurons rather than the tens of thousands of artificial neurons from the previous solution. And look at how clean the attention map is. It is focused on the road horizon and the sides of the road at the road horizon, which is how people drive. So this solution is focused on the task rather than the context of the task. And because the liquid network solutions are much smaller, we also understand how they make decisions. We can take the activity of this machine learning model, this AI model, and map it onto a decision tree that explains how the decision is made. So how did we do this? How did we get from such a lot of neurons to so few neurons? What is the difference? How is this performance possible? Here's what happens inside a liquid neuron. Now, in most traditional AI solutions, the artificial neuron is an on-off computational unit. This means the neuron takes in some numbers, adds them up, applies some basic math, and then passes along the result. And the result is on-off. In other words, it's 0 or 1. And this kind of computation becomes very complicated because it is happening across tens of thousands of nodes or artificial neurons. Now, contrast this with the liquid solution. So liquid networks use fewer neurons, but each one of them does much more complex math. And these neurons are not simply on-off switches. which is how the artificial neurons function. So specifically, we use differential equations that are inspired by what biologists determined happens in the neurons of worms. And we also use differential equations on the weight of the connection on the synapse. When we take the math of the synapse together with the math of the artificial neuron, and we do some basic algebra on these two equations, we get the equations we see at the bottom of the screen. And these equations are actually extraordinary because they really tell us that something very special happens inside the artificial neuron of a liquid network that enables that neuron to adapt after training based on the inputs that it sees. And if you're curious which aspect of math is responsible for this adaptation after training, you can ask me questions after the talk. This is actually important because most AI solutions are frozen after training. So today's solutions get trained once, and then they get deployed. And then if you try to use an improved solution, you have to wait for the next release. But because of what is happening inside the artificial neuron of the liquid network, and also because of how these neurons are wired, these solutions are able to adapt after training based on the inputs that they see. So let me explain how this works with an example. We trained traditional AI solutions, all kinds, and liquid networks to find things in the woods during the summer with unlabeled videos like this one. And so interestingly, all the models learned to do this task in the summer. But then we tried to use these summer-trained models in the fall. And let's see, so here is the deep neural network, the traditional AI model, which fails because the new background confuses the model. Just look at the attention map. This network doesn't understand where to go because the background is so different. On the other hand, the liquid network is so focused on the task. As soon as it sees the object, it locks in on it, and it knows that it's its target. And look at how clean the attention map of the solution is. It turns out that the same model that we trained in the summer can also work in the winter, and it also works in urban areas where the object moves, where the object is no longer stationary. And so this is because of the adaptation capability that is built inside the model. So this is the same model that was trained in the woods in the summer that is now used in a completely different area with a mobile object rather than a static object. So it turns out that we can use this technical approach to all kinds of problems. Here we show surgical face recognition for cholecystectomy, and liquid networks, again, perform much better than the existing methods. So liquid networks use differential equations as their foundational computational model. This means that they're good for applications that are based on time series data. And so sensors, video, financial transactions, weather reports, text, because you can think of text as a time series of words. All of these are situations or data types where liquid networks do well. We compared liquid networks against transformers in physical real-world dynamics modeling, and their performance was 123% better than that of transformers. We compared them in many other tasks. So in sequential image processing, we achieved 46% improved accuracy. In text sentiment analysis and information retrieval, we had 11% accuracy improvement, which is really high for text retrieval. We also looked at how they perform on sequential long-term signal classification. Again, 30% improvement. And this is one of my favorites. If you want to use machine learning to predict your vital signs, then you will have 33 times improvement in accuracy over transformers with this technology. And this actually shows you the versatility of our solutions. And in fact, in about 2 weeks ago, the company we started building about a year ago using this technology released its first series of foundation models. We call them liquid foundation models. And here you can see the performance of liquid foundation models with different numbers of parameters, specifically 1 billion parameters, 3 billion parameters, and 40 billion parameters, although effectively we only use 12 billion of those. And you see that performance against the open source models that are in the same class size. And we see the performance on a benchmark called the MLU Pro benchmark, which measures these models' ability to reason. And so you can see significant performance improvement over the state of the art. You can also see here the memory footprint of liquid foundational models. So it turns out that liquid foundational models have a reduced memory footprint compared to transformer architectures. And this is particularly true for long inputs, where the cache in transformer-based liquid large language models grows linearly with a sequence length. But by efficiently compressing inputs, the liquid foundational models can process longer sequences on the same hardware.
Daniela,
so, yeah.
I love for the audience, that's a pretty significant looking chart. And same with the previous one of smaller models that are outperforming larger models. So for those that are familiar perhaps with ChatGPT and maybe some of the transcription and some other elements of AI, this has an impact depending on the parameter size and the task at hand. What implications does this have? Is this for maybe those professional and personal use cases, but also considering hardware and software limitations of the robotics industry?
So first of all, you get better performance, you get higher quality results. But equally important is that these models are much more energy efficient. In fact, they are about 1,000 times more energy efficient for both training and inference. And because of this lower memory footprint, we end up with performant models that can fit on company computers, on enterprise computers, that can run on edge devices like sensors and robots, that can run on phones. And so from a business point of view, this approach to machine intelligence, this approach to AI will give you a solution that does not require cloud calls, that does not make any cloud calls. In other words,
you call that hybrid intelligence then? Because I think there's a lot of concerns right now and in the media about all the energy consumption that AI is going to require. So this seems like maybe something people aren't really thinking about is major advancements here that could offset that just from a computational level, let alone the second order impacts that could occur from this technology being deployed.
So that is absolutely right, Zeno. This is a solution with a low energy footprint that costs less, that has a lower carbon footprint. And in addition to that, it's a solution that you can run internally within your company. You do not need to give your data to the big 5 providers of foundational models. You can keep the data in house because you can have these models run in house. If you remember, some of the first slides of this talk essentially said we want models that do not make mistakes and that fit on small computers. So here you can see performant models that fit on small computers. And because of the smaller memory requirement in this chart, you can fit this model on your phones. You can fit these models on your enterprise computers. You can fit these models on other edge devices. And as we continue to scale up foundational models and use them more extensively, the inference side of energy consumption will become increasingly important and frankly overpowering with the energy costs, because for training, you do training once, but inference for one query, you might follow up with lots and lots of additional clarifications and follow-up queries. And if you get 1,000x savings in energy for each of those queries, you can see how it all adds up. There will be more information about these models. So I guess maybe I should make a clarification here. I've inserted some performance numbers from the company products, Liquid AI. Liquid AI will have a formal product launch on Wednesday. And if you go to the website of Liquid AI, it's just liquid.ai, you will be able to sign up for the streaming of the presentations if you cannot come for our presentations in person. Let me move on because I have a lot more material to cover. So I have a few more examples of performance. And so here, for instance, you can see that the liquid foundational model with 1 billion parameters achieves the highest scores across many benchmarks in the 1 billion parameter category. And so in this small model category, this actually shows you that we have a new state of the art. And so this is also the first non-GPT architecture that significantly outperforms transformer-based models. And here, if you look at the liquid foundational models with 40 billion parameters, you see a new balance between model size and output quality. In this case, our model only uses 12 billion activated parameters, and its performance is comparable to models larger than itself. And so that's really exciting. And here you can see how we have optimized our models to deliver a best-in-class 32K token context length. And this is pushing the boundaries of efficiency for this size. We are very excited about the possibility of using liquid foundational models for a wide variety of data modalities, including text, including video, including audio, including financial transactions, and anything else that comes in a sequence. So how can we push capability in this using these new ideas? The ability to handle efficiently text and sensor signals brings us another benefit. And here, the benefit is that we can go back to control tasks in the physical world and consider how language contributes to intelligence, and explore a triad between perception, language, and action as the basis for intelligence. Because language allows us to raise the level of abstraction and reasoning that is possible for intelligent machines. Typically, if you want a self-driving car to safely navigate around this deer, you would have to analyze every pixel and every XYZ coordinate in this image. The question is, can you think about it at the level of avoid the deer instead of worrying about pixels and XYZ coordinates? So let's say we have an image and some text describing it. What we can do is we can build a foundational model that aligns the perceptual features and the language features of the scene in the same space. And then we can train a model to control relative to some concepts. For example, avoid the deer. And using language, we can then say with words without additional training, now also avoid trees and other cars. And this is extraordinary because it means that we do not need to train in such an extensive way. We can obtain this out of distribution generalization at the level of abstract concepts that are stated in words. And here's more specifically how this works. First, we find a set of textual features that are relevant to driving. Then we curate a set of textual features to be swapped in as simulation targets. And finally, we simulate the image features by sensibly swapping in with the target features. And so that means that we can train a vehicle to drive in one scenario, and our method directly generalizes to a diverse, extensive, out of distribution set of scenarios in a closed loop control setting. For instance, we can train to avoid other cars, and then our method generalizes to say, now you can also avoid deer. And we can also train with certain weather characteristics, for instance, summer, dry day, and avoid cars. And then we can say, okay, now also drive in rural environments or in urban environments, drive at night, drive when it's snowing, drive when it's raining, avoid other animals, avoid benches, and so forth. So this is really exciting because it really gives us this ability to do out of distribution generalization and reasoning based on language. And this improves the capabilities of our systems. And it gives us out of distribution generalization, which you may have heard of. That means running the model in completely different scenarios. So now that we have AI that can think in such profound ways, we can also begin to ask what kind of machines are we able to create? And the body of the machine is really the second aspect of physical intelligence. And so I'm sure that by now you generated images from text using systems like GPT or DALL-E. So it turns out we can also do text to robot, but not using today's AI solutions, because today's AI solutions work on statistics and they do not understand physics. And so here's an example. I asked GPT to help me draw a new research robot concept, a schematic for a robot that can pick delicate fruits off of trees. And these are some samples of what we got. And so I have to say, these are all very creative. And I love the colors and the patterns. The graphics are wild and cool. But let's look more carefully at whether these robots can actually meet their specifications. I like the strawberry. So if we look at the strawberry in greater detail, first we see that the stem on the top seems to defy physics, since it is thin and seemingly brittle, and it cannot really hold such a big weight. And then moreover, if we fix both ends of the mechanical arm, we do not have much functionality. And finally, it's how are we even going to fabricate the kind of strawberry skin that we have there? It's really complicated. And so this is what you get with today's AI solutions. Now, with our solutions in my lab, we have an AI system that guides the design process by checking and simulating physical requirements. And so you start with a simple language concept, such as make me a robot that can walk. And our system generates the design. This includes the shape, the materials, the actuators, the sensors, and also the program required to control the system and the fabrication files to make it. And then using a physics simulator, the designs keep being refined and optimized until they satisfy the task requirements. The physics simulator ensures that the designs meet the laws of physics, and then the task requirements get further refined using a stable diffusion-like process. So you might get a blob, and then later on, you might get a robot that begins to look like a walker with legs. And so within hours, you can go from idea to a controllable physical machine. We can also use this approach to design a robot that can pick things, and we can use a robot that can move an object like this finger, and we can even get a walking teapot. All these going from concept to a realizable prototype using language and using an AI reasoning engine. We can also do image to robot. So this photo can be transformed into a cuddly robotic bunny. And to do that, our algorithm computes a 3D representation that can then unfold it, and it gets, that can get, sorry, so the 3D representation gets sliced into layers that get unfolded and printed. And then we take the printed layers and we fold them. We string some motors and sensors. We write some code for controlling the motors, and we get the bunny in this video. And this approach can be used to make anything from a photo. So what's exciting about this is that we can use AI to do text to robot or image to robot. And this drastically reduces the time and resources needed to prototype and test new products. And this allows for a faster innovation cycle. And now that we can get the robots to think in ways that fit on physical machines and fit with the physical requirements, and we know how to quickly design new machines, we can also get these machines to learn, which is the third aspect of physical intelligence. And specifically, these machines can learn from humans using data about how humans do tasks. You can think of this as doing human to robot. So in our lab, we created a kitchen laboratory for kitchen tasks. And we instrumented people with sensors. And then we record pose, muscle, even gaze when people perform kitchen tasks. We need this kind of physical data in order to understand the forces and the torques, in other words, the dynamics of the interactions when people perform the tasks. Many people these days try to learn how to do things by watching videos, but videos do not capture the dynamics of the interaction, so we need to do more. Okay, so we collect all this data, and then we use AI to learn from this data how to get robots to perform those tasks. And the end result is machines that look less mechanistic, machines that move with grace and agility, as well as adapt and learn. And this is what I call physical intelligence. And so we can teach robots to perform complex tasks that are difficult to model using math. And we do so by using data collected from how humans do those tasks. So the ability to turn photos and words into functional machines, coupled with using liquid networks to create powerful brains that can learn from humans, is incredibly exciting, because it means we can build almost anything we imagine. Today's statistical solutions have a ceiling. These solutions need server farms. These solutions are not energy efficient. They are not sustainable. They make inexplicable mistakes. But when we use liquid networks and physics-based intelligence, we have the opportunity to imagine so many ways in which robots interact with people. I believe in the future we will have personal assistants that optimize our routines and anticipate our needs. We will have bespoke machines that help us at work. And we will have robots that delight us in our spare time. And so this is the promise of physical intelligence. It is to transcend our human limitations with capabilities that extend our reach, amplify our strength, and refine our precision, and grant us the ability to interact with our world in ways we've only dreamed of.
Thank you, Daniela. That I think, and I hope everyone learned a lot from that. I would want to elaborate and double click on, there's kind of two huge changes happening now, and you've been in the robotics world for years now. And I want to highlight and double click on the design element and the learning element. What is combining those two major advancements? What does this mean for the broader global robotics ecosystem, and also the global and diverse artificial intelligence ecosystem, the semiconductors, cybersecurity, sensors? There's a lot of components that come into play when these eventually are scaled out. Maybe where do you see that the robotic world today, and where do you see it heading over the next 10 years as these technologies come together?
That's an excellent question. So I think it's really important to understand that for physical work that is done by robots, we actually have two important components of the machine. We have the body of the machine, which is important because the body can only do the capabilities, can only have the capabilities it was designed for. A robot on wheels will not climb stairs. So you really need to think about the tasks that the robot has to do and then build a body that has the capability of executing those tasks. And then you also need the brain of the machine, and this brain needs to have the computational power to control the body to do what it's meant to do. Now, with the advancements in AI, and especially the connection between AI and the physical world, we will be able to design custom robots much faster, because right now it takes months and sometimes years to iterate the design of a machine when you do it from scratch. So this kind of computational approach to design and fabrication has the power to greatly reduce the design cycle, and that in turn will bring us more products, more custom products that are tailored to a wider range of tasks. But these robots are currently pre-programmed. And so as a result, the robots are primarily capable of doing the simple tasks for which we can write algorithms from scratch. By learning from people how to execute tasks, we will be able to get machines with a wider range of capabilities and much more complexity and ability to adapt to the world than what we see in today's machines. And this actually opens the door to having robots that are safer and more likely to support people in their human-centered environments.
So it sounds like there'll be a lot more robots in our future.
I certainly believe in this view of the world, and I really believe in having robots as tools that support us with physical tasks, along with AI, which is a tool that supports us with cognitive tasks.
Okay. And before we go on to the rest of Q&A, final poll, I think it's showing to people is do you plan on adding or initiating a position in any of the following thematic areas in the next 6 months? So A, robotics and automation, B, artificial intelligence ecosystem, and 3, healthcare innovation. And I'll leave that up for a couple more seconds, and we'll see where that's at and then dive into the rest of Q&A. So if you have any more questions, send them now as well. Okay, Q&A. Daniela, we have a question. Europe and Japan have made decades-long inroads into the research of robotics. Can you speak to the competitive landscape from abroad?
Yes, indeed. There has been a lot of funding directed at research in Europe and Japan. And I would say that Japan is really strong on the hardware piece. So Japan has been the first to commercialize at scale the robots used in industrial automation. And because the population in Japan is decreasing, Japan has been investing in the development of highly capable robots that can help with what they call the silvering society, a society where there will be a lot of retired people and not so many human workers to help them. And so this vision that the human workers will be augmented by machines for productivity and efficiency purposes has driven a lot of the research in Japan. Japan is also beginning to expand in AI, but traditionally the focus in Japan has been on the hardware side. And the vision and the masterpieces of engineering that are being deployed in Japan are extraordinary. In Europe, there has been a really strong push towards developing the science and engineering of intelligence. Europe has created a lot of centers that look at how to connect natural intelligence with artificial intelligence, meaning how can we study how can we enable progress in neuroscience and in artificial intelligence, and how do they leverage off of each other? Because the more we understand about nature, the more likely we are to build models that are inspired by nature and push forward the capabilities of machines. In the US, we have a broad approach to developing all aspects of machine intelligence. And in fact, liquid networks are an example of looking toward nature to come up with a new approach to artificial intelligence. For robots, we need good bodies and we need good brains. And we need brains that can run on the body of the machine in order to make the most out of the capabilities of AI. And so we have a lot of efforts towards computational design and fabrication of robots, like the ones in my group, but there are other efforts in the labs of my friends, in other laboratories in the US and around the world, but also to make robotic brains that can help robots do more complex tasks, that can help robots be more intelligent.
You had started answering this with the other question about Japan and their demographics, but what robotics are being developed to help seniors manage their older lives and remain independent longer? And I think you've covered that there's different form factors and that can be used for predicting healthcare data and things like that. So I think the advancements here are, very broad in scope and synergistic, but maybe if you have some examples of where you've seen some or believe there will be some positive impact.
Another important area in robotics that will help us with robots that could work side by side with people is soft robotics. Today's industrial robots, and frankly, most robots built today, are actually made out of hard metals. And if the robot makes an error, or if you're in the way of the robot and you get hit by it, that's actually a bad thing because you will get hurt. By building robots out of softer materials, we will have safer robots to be around.
Like a strawberry.
Also, there is a lot of effort these days in building humanoid robots, in building robots that have the form factor and the size of a human. And the thinking there is that if we want companions, if we have a machine that is built to mimic our size and our capabilities, might be like a teammate that can help you, I don't know, maybe fold a big sheet for which two hands are not enough, or that could do things for you in an autonomous fashion in the home. The way I see robots coming into our lives is in three modalities. So robots can assist us, robots can augment us, and robots can do things on their own. And depending on which modality we imagine the application to be in, we might need human factor or human shape forms, or we might need other types of forms. We have a lot of robots on the highway in the form of the Waymo and Cruise vehicles. So now let me underscore that I do not believe we're ready for robotaxi, which is why we don't have those vehicles in Boston and they're not widely spread in New York. And that's because the control system and the sensor systems of these robots is not robust enough to cope with the chaos that we have in our roadways. But these robots on wheels can do so many things in other environments. They can move containers in ports to speed up and introduce efficiencies in our logistics and transportation.
That's a hot topic right now, too.
Exactly. They can also help in factory yards, in hospitals, in any environment where things don't move as fast and you don't have too many things that move at the same time. And so today's technology, today's self-driving technology is suitable for industrial applications that are not on public roads.
Yeah, I think we're at time, and that makes sense. So I think, it seems like to wrap that thought up, like right now, industrial robots are here, but soft robotics, better designs, better learning, we'll have more robots in our homes, but that's not today yet. We're still at the Roomba. I think we're at time. Thank you, Daniela, for joining us today and sharing your wisdom with everyone about what's happening in robotics and AI and what you're actually building in practice. Thanks, everyone, for joining us. Hope everyone has a great day. And obviously, tune in to the Liquid AI launch later this week. And yeah, thanks, everyone, for joining us.
Thank you very much. Bye-bye.